Lecture 14.4, we're going to be talking about the normal distribution. And this is a lecture for MGF 1106, Liberal Arts Math. And my name is Jorge Young. So the objectives for section 14.4, again, this is the normal distribution. So we're going to understand the basic properties of the normal curve. And then we're going to relate the area on the normal curve to z-scores. And then we're going to make conversions between raw scores and z-scores. And then we're going to use the normal distribution to solve some applied problems. So the first thing is, what is the normal distribution? And so a simple definition would be that the normal distribution describes many real-life data sets. And the histogram shown gives us an idea of the shape of the normal distribution. So on the left, we can see a histogram. And so one thing about the normal distribution is that the mean, the median, and the mode are all the same. And the normal distribution, you might have heard about it, what they call is the bell curve. And as you can see, the line here on the right, it looks like a bell. So the normal distribution. So mu is the mean, and what happens is that mu actually divides the data set into two equal symmetrical parts. So right in mu, if this was a sheet of paper, I can actually fold them, and they will fold onto each other, and so because they're actually equal. So the nice thing about this is that 50% of the data points will be to the left of mu, and 50% of data points will be to the right of mu. Now, in the previous lecture, we talked about standard deviation. Here we have sigma. And if you recall from the first lecture, mu is the population mean, and sigma is actually the standard deviation for the population. So here we have mu minus sigma, mu plus sigma. And if you notice that 68% of the data points fall within plus or minus one standard deviation of the mean. Now we have mu minus 2 sigma, mu plus 2 sigma, and now 95% of the data points fall within plus or minus 2 standard deviations of the mean. And then the last one is mu minus 3 sigma and then mu plus 3 sigma. And so 99.7% of the data points in a data set fall within plus or minus 3 standard deviations of the mean. And this is what we call the 68, 95, 99.7 rule for normal distributions. And so these rules allow us to make a lot of inferences based on a data set, if you will. So some of the properties of a normal distribution. The normal curve is a bell shape. The highest point on the curve is the mean of the distribution. The mean, median, and mode of distribution are all the same, so they're equal to each other. The curve is symmetric with respect to its mean. The total area under the curve is 1. And then roughly 68% of data points are within 1 standard deviation from the mean, so that's plus or minus 1. 95% of data values are within plus or minus 2 standard deviations from the mean, and then 99.7% of data values are within 3 plus or minus standard deviations of the mean. And again, mu is the population mean, and sigma is the population standard deviation. So here's an example. Suppose that the distribution of scores of 1,000 students who take a standardized intelligence test is a normal distribution. Now, standardized intelligence test, that's not a good measure of anything, so but it's a good example to use, if you will. So if the distribution mean is 450 and the standard deviation is 25, then we have an A and a B. So A, how many scores do we expect to fall between 425 and 475? And how many scores do we expect to fall below 500? And the nice thing is, once it tells us that it's normally distributed or is a normal distribution, then we can use the 68, 95, and 99.7 rule to find the data points. So here's the solution. So 425 and 475 are each one standard deviation from the mean. And so therefore, approximately 68% of the scores lie within one standard deviation of the mean. So again, the mean was 450, and they told us that the standard deviation is 25. So 450 minus 25 gives us 425, and 450 plus 25 gives us 475. And so that's how we get plus or minus 1. And so therefore, we expect that 0.68 times 1,000, because we had 1,000 scores, So that gives us 680 scores. So 680 of the 1,000 people who took this IQ test will fall in the range between of scoring a 425 and a 475. Now the next one is the 500, right? So now we know for a fact that 5% of the scores lie more than 2 standard deviations above or below the mean. And if you recall, plus or minus 2 was 95%. So at least 5% either below or above. Now, so we expect 0.05 divided by 2 or 0.025 of the scores to be above 500 because we have 5%, but we have to divide the 5% by 2. So that gives us a 2% and a 2%. And so multiplying by 1,000, we can expect that 25 scores are going to be above a score of 500. Now, the next thing we want to talk about is z-score. So the previous example, what we did is we used just the raw scores that we had, but we can actually standardize scores. And a standard normal distribution is simply a distribution that has a mean of 0 and a standard deviation of 1. Excuse me. So in the next slides, we have some tables. And these tables give us the area under a curve between a mean and a number called the z-score. So a z-score simply represents the number of standard deviation a data value is from the mean. So for example, for a normal distribution with a mean of 450 and a standard deviation of 25, the value 500 is 2 standard deviations above the mean. That is that a value of 500 corresponds to a z-score of 2. So how do we convert raw scores to z-scores? So the formula is that z is equal to x minus mu divided by sigma, where x is the data value, sigma is the population mean, mu is the population mean, and sigma is the population standard deviation. So this is how we standardize scores. Now, we convert values in this key point is that we're going to convert values in a non-standard distribution to z-scores. And we can do that as long as it's normally distributed. So here's an example, converting raw scores to z-scores. So suppose the mean of a normal distribution is 20 and the standard deviation is 3. So A and B, we're going to find a z-score that corresponds to a raw score of 25. And then we're going to find a z-score that corresponds to a raw score of 16. So here we can see the image. So we have a mu is 20, the sigma is 3. The raw score is 16, which is below the mean, and a raw score of 25, which is above the mean. Another thing that we'll talk about on the other slide is that if a raw score is below the mean, then their z-score is going to be negative. If the raw score is above the mean, then the mean score, the z-score is going to be positive. So for the first one, we have x is 25, mu is 20, and sigma is 3. So we use the formula and we get that it has a z-score of 1.67. That makes sense because it's above the mean of 20. So 25 is above 20, the same way that 1.67 is above 0. And then the other one is that we have that x is 16, mu and sigma are the same, so we have a negative 1.33. Again, 16 is below 20, and negative 1.33 is to the left of 0. So here's another example. Suppose you take a standardized test. Assume the distribution of scores is normal, and you receive a score of 72 on the test, which had a mean of 65 and a standard deviation of 4. What percentage of those who took this test had a score below yours? So the first thing is, since the mean is 65 and you scored 72, then your z-score is going to be positive because you actually scored above the mean. And we have a standard deviation of 4. So we're going to use this information to find the z-score. And we get that your z-score is 1.75. And then using the table, and I'll provide the tables, and it should be in the textbook also. But using a table, we have that A is equal to 0.460 when Z is 1.75. Now the normal curve is symmetric. So 50% of the scores fall below the mean. I mentioned this earlier. So then therefore, 96% of the scores in this particular test are below a 72. So you scored above 96% of the people who took this particular test. Now let's consider the following information. In 1911, Ty Cobb hit a 420. The mean average was 0.266 with a standard deviation of 0.0371. 1941, 10 Williams hit a 0.406. Mean average was a 0.267, standard deviation of 0.0326. 1980, George Brett hit a 390. The mean score was a 261 with a standard deviation of 0.0317. So assuming normal distributions, and this is a big assumption, another way that you might read this is that the distribution is normally distributed. We're going to go ahead and use z-scores to determine which of the three batters was ranked the highest in relationship to his contemporaries. So here's the solution. Ty Cobb had a z-score of 4.1506. Ted Williams had a z-score of 4.2638. And George Brett had a z-score of 4.0694. So compared with his contemporaries, Ted Williams ranks as the best hitter. So it's hard to compare, let's say, Cobb to Williams or Williams to Brett, just merely looking at their averages, because we don't know what the competition was. Was it better during Ty Cobb's time or Williams' times or Brett's time? So z-score allow us to determine or make a determination, and it removes some of the bias. So here's another example. Manufacturer plans to offer a warranty on an electronic device. Quality control engineers found the device has a mean time to failure of 3,000 hours and a standard deviation of 500 hours. Assume that the typical purchaser will use the device for 4 hours per day. If the manufacturer does not want more than 5% to be returned as defective within the warranty period, how long should the warranty period be guaranteed? So we need to find a z-score such that 95% of the area is beyond this point. So this score is to the left of the mean and is negative. Now by symmetry, we find a z-score such that 95% of the area is below this score. And then 50% of the area lies below the mean. So our problem reduces to finding a z-score that's greater than 0, such that 45% of the area lies between the mean and that z-score. So if A is 0.45, the corresponding z-score is 1.64. So 95 of the area underneath the standard normal curve falls below a z-score of 1.64. And by symmetry, 95% of the values lie above a z-score of negative 1.64. So since z is equal to x minus mu divided by sigma, we obtain that negative 1.64 is equal to x minus 3,000 divided by 500. That gives us an x of 2,180 hours. So owners use the device about 4 hours per day, so we divide 2,180 by 4. We get 545 days. This is approximately 18 months if we use 31 days per month. So the warranty should be roughly 18 months long. And that's the end of section 14.4. Thank you.